Hi, the name of this course is Sensors, Wiring, and Troubleshooting, and so far we have talked about digital multimeters and volt-ohm meters in the sense of troubleshooting and the effect that a meter can have on a circuit while you're troubleshooting. We've talked about the basic push-button switches and regular switches and some relays. In fact, you've already wired a relay, or will be at least by the time you've watched these videos. And now we're going to get into the actual sensors. And I'm going to start with photoelectric sensors. You'll see I have inductive and capacitive grayed out on here. That's because we're going to cover those the next time around. But let's start with photoelectric sensors. So sensors are used in all types of automated manufacturing systems, and they provide the eyes and the ears, the tongue, the nose to the controllers, like the PLCs or the PACs, as programmable logic controllers or programmable automation controllers. And I love this graphic. This graphic came from a textbook titled Programmable Logic Controllers. It's written by Frank Petrozzella and published through McGraw-Hill. It's really a very good text, and the third edition that it came from is not the latest edition. His later editions, and I'm not selling it, but I want to make credit where credit is due. His newer edition is also very good. So if you're interested in programmable logic controllers, you probably want to take a look at that text. So let's look at sensors. Photoelectric sensing and a photoelectric sensor is nothing more than an electronic device that responds to the change in light intensity falling on a sensing head. The very first devices that were used for photoelectrics are photocells. And I'm showing a photocell down here in the corner. You can see it has some elements on it that are solid state in nature, and there's just 2 pins on it. And the earliest photoelectric sensors was nothing more than a photocell and a light bulb. And the light would shine onto the photocell. The photocell changes resistance depending on the amount of light that strikes the photocell. You could detect the change in resistance and thereby have the controller perform an action based on that change. These photocell light bulb combinations for photoelectric sensing were called non-modulated. The gain, and sensors have gain, we'll talk about that later. The gain of the non-modulated sensor is limited to the point at which the receiver can recognize ambient light. Because the problem with a photocell and a light bulb is that we have ambient light up here. So we might have some lights up here from our room shining down. And these ambient lights can affect the resistance of this photocell, and it may not see the light from the light source because it's seeing the light from these ambient type room lights. So you had some problems with that. So it's only worked well if you could shield the receiver. Notice the word I just used there. This is the receiver. So the photocell is the receiver because it's receiving light. So it only worked if that receiver can see the light from what's called the emitter. And the light source out here is called the emitter. Together, these were called an emitter-receiver pair. They have some advantages to them. The biggest advantage is getting rid of the ambient light. I can go through a fairly large explanation of all some of the disadvantages, but you know, these things are, even though they're used yet, they're not used in great many. So there are these sensors in photoelectric world called ambient light receivers. And an ambient light receiver is nothing more than a non-modulated type photoelectric sensor that still uses a light bulb and some sort of photocell or maybe a phototransistor, which we're going to be talking about shortly. So ambient light receivers are really good if you're detecting things like red hot metal or glass when it's really hot. Emits large amounts of infrared light, and the light coming from these items is usually much more powerful and much more intense than the ambient room lighting. So therefore, these ambient light receivers work really well in the environment whereby the product you're trying to sense is really red hot and throws off an enormous amount of light. The other place that they're used is in open frame conveyors. Now, an open frame conveyor, for those who are fairly new to the automation world, is a conveyor whereby on the top of the conveyor you want to have a solid belt. You might have two straps for a belt, and product comes down, and then there's an open space right here that's open. You can see the floor down through the bottom, and what they'll do is they'll mount an ambient light sensor below the conveyor so that when product comes across the top of it, it literally blocks out the ambient light or the room light, and therefore you can sense if there's a product or a box or whatever on that conveyor by blocking out the room light from the sensor. They work really well. Well, in the 1960s, solid-state electronics started to become more prominent, even though it was invented actually in the 40s. It really started being used commercially and industrially in the 60s. And this wonderful device called an LED came out. And LEDs are nothing more than a diode, and they work exactly like a diode, except that they emit a very small amount of light. I'm sure you all know what an LED is. Today they're in our stoplights. You can buy LED room lighting. They're all over the place. But a single LED puts out a very small amount of light. And they come in various colors. They come in red and green and amber and blue and infrared. I've seen the white, and I've seen the soft white. So they come in a lot of different colors, a lot of different shapes, a lot of different sizes. But again, an individual LED puts out a very little amount of light. There's also a replacement for the photocell, and that's a phototransistor. A phototransistor is a solid-state device. You can see the symbol on this looks very similar to the transistor that we talked about in our last lesson. It has a collector up here, just like a regular transistor. It has an emitter lead, not to be confused with the emitter of a photoelectric sensing pair. But notice the base lead here is gone. And instead of a wire, the base, this has a photosensitive type material here, and there'll be a lens on top of this, and this base connection becomes light. So it uses light to turn that transistor on and off. So what did I mean? Since we had non-modulated sensors, what do we do with an LED sensor to give it some distance? Think about an LED, just one single LED. You can't send that light a large or a far distance, and you want to keep these sensor packages somewhat small, so you don't want to put a big LED light bulb in there either. So what they'll do is they modulate the LED light, and these are called modulated LED sensors. What they'll do with the modulated LEDs is, if you look down at the bottom here, this right here is the emitter. And in the emitter, it has its own regulated power supply, which gets fed from an external power source, and there's something in here called an oscillator. And the oscillator is something that produces an AC signal. But this AC signal is going to be a square wave. So it's turning on and off and on and off. So you got this on and off from 0 volts to whatever the plus voltage is. And it's the frequency of it, and the frequency is measured from here to here. That would be 1 cycle or 1 hertz. Or the frequency can be switched in the kilohertz range. Now you can't switch an incandescent light bulb that fast because the filament needs time to heat up, to light up, and the filament needs time to cool down in order to turn off. But an LED is instant. You turn power on, it's lit. You turn power off, it's not lit. So you modulate them by switching the light on and off and on and off and on and off. And I'm going to pull just a number out, and this number's I'm pulling out of the air. So let's say that this is running at 2 kilohertz. So I'm turning this LED on and off, on and off, on and off at a rate of 2 kilohertz. The light's coming out. Over here is the receiver. And the receiver has a phototransistor. There's an amplifier here to amplify the signal. It also has a regulated power supply. And there's something in here that's then called a demodulator. Now this amplifier is tuned. So it's tuned. And it happens to be tuned so that it can only see the frequency of this LED. So this amplifier will only see light that's turning on and off at 2 kilohertz. Therefore, it's not going to see ambient room light. It's not going to see other LEDs. It's only going to see an LED that's turning on and off at a 2 kilohertz rate. All of a sudden, I can get large distances off of these sensors, whereby I can place them, feet to yards from each other and still have them see the light from the receiver or from the emitter. This is basically how your TV remote works. Your TV remote is infrared. It uses an LED. And depending upon what button you press on your TV remote, the frequency of the modulating of the LED is different. So if you press the number 5 key for channel 5, it may be at 2.1 kilohertz. But if you press channel up or volume down might be 3 kilohertz. And at your TV, the receiver has a demodulator with a whole series of tuned amplifiers that can then detect which frequency is being sent from the remote and then performs the function that the remote says. That's also why you could buy a universal remote. And if you've used a universal remote, you have to teach it, or you have to enter a code in for your particular television or DVR or DVD player, because you're telling the remote, these are the frequencies I want you to use for each one of the buttons. So photoelectric sensing has several different modes of operation, and there's probably even more than these right now, but the main modes are opposed mode, and opposed mode sensing is really what you might hear as break beam. Break beam meaning that you have a light source and you have a light receiver. So you have an emitter receiver, and the object that you're sensing actually breaks the beam of light. It's called opposed mode. There's also retroreflective mode, which uses a light source, an emitter, but it has a reflector, just like on your car, only these reflectors are usually white or silver. And then there's proximity mode. And under proximity mode, there are 5 subcategories. The first one is diffused, then divergent, convergent, fixed field, and fixed field is sometimes called background suppression mode, and adjustable field. So let's talk about each one of these. Let's talk about opposed mode. By the way, I would like to thank Banner Photoelectric Engineering. I've borrowed these photos and graphics from the Banner Photoelectric Handbook. Banner and a company called Keonce and Turk and another company called SICK. They're very popular brands of sensors. I would suggest you research many of them, and the companies are very helpful if you have any questions. So opposed mode sensing, it's called break beam. Another term that is sometimes used is direct scanning mode, and in this mode you have an emitter and a receiver that are in separate housings. So these are each separate housing. They're positioned opposite of each other so that the emitter, which is nothing more than a light source, sends its light out to the receiver. When an object, and here's the object that we're going to be sensing, moves in and breaks the beam, the output of the receiver turns on or off, depending on the setting, so that you can get a signal at the controller to say something is breaking the beam, something is present. You've probably seen these when you walk into a store. Sometimes they'll have emitter receiver pairs on each side of the door. Your garage door opener at home may have opposed mode sensors mounted down toward the base to let the garage door opener know if something is standing in the way and not to operate the door. They work really well. In fact, photoelectric sensors, no matter what type they are, will work and work efficiently only if you break what's called the effective beam. The effective beam, and you can see it here, is what is filling the lenses of this emitter receiver. You have to block the entire effective beam before the sensor will sense. You see that we have a radiation pattern from the emitter, so light's coming out in all directions, and then the receiver has a field of view, so the receiver can see at a variety of angles. But the effective beam is the beam of light that comes between the emitter and the receiver, and that beam has to be totally broke. If you only break this much of the beam and have that beam, it's not going to sense. So again, the entire effective beam has to be blocked for a sensor to work. You can shape the effective beam. You can have an emitter that has a large lens, a receiver that has a small lens, or vice versa. And now I've got an effective beam that is shaped as a cone. So you can shape it to different sizes, to different shapes, depending on the product that you're trying to sense. You can also put something called an aperture on one of the lenses, on both sides of the lenses, to help you shape the size and shape of the beam. And I use an example, like if you had a sensor this size, but you're trying to sense a product that's fairly thin, where you're not going to break, and let me try to put it over here on top of this, where you're not going to break the effective beam, you can put an aperture on the front of this so that it will break the effective beam. So maybe if I use this one, I can have my product come in there and still break the effective beam. So you can get apertures. I've even seen people use black electrical tape to tape over the lenses to form and shape a beam. Or cardboard with a cutout in it. But for permanent installations, you definitely want to contact the manufacturer and get an aperture made that snaps and fits right on to the sensor that you're using. Retroreflective mode, simply called reflex mode or retro mode, has an emitter and receiver in the same package. So this package here has both the emitter and the receiver. So the light is sent out, and retroreflective means that there is a reflector at this side. They call it a retro target. The light from the sensor reflects off the reflector and comes back into the same housing, and where the receiver can be seeing the light. So it's just like an opposed mode sensor, where you still have to break the beam because this product is going to be sliding through here or traveling through there. You have to break this beam in order for that sensor to sense. But this time you only need a reflector on one side, and the emitter and the receiver are in one housing. You can also shape the size and shape of the beam with a retroreflective sensor, because you can change the size and shape of the reflector. This is showing a round one. You can get a smaller round one. You can get square. You can get reflective tape that you can shape the tape differently. That's an odd pattern there, but just to show you that that would be the shape of the beam. And as long as the light coming out to the reflector is completely broke, if this effective beam is completely broke, the sensor will still sense. Now about the reflector. A good reflector is going to return about 3,000 times as much light as a standard white piece of paper. That's one of the reasons why a retroreflective sensor will only recognize the light coming from its emitter. I've used a sheet of paper, I've used a white object, and it works. But if it's not as reliable, it doesn't work as well as when you use an actual reflector. Again, they should be white or a silver type color, not red or amber or anything like that. Retroreflective can also be used to sense shiny objects. If you think about it, if you've got a product that's shiny and you've got an emitter receiver down here that's putting out a light signal and receiving its own light, if I've got a shiny object and I mount that sensor this way, the light will come up, hit the shiny object, and come off the shiny object and come right back again. It won't even see it. The sensor will never know that the object is there. But there's ways that you can mount these so that what you can do is put the reflector and the sensor at an angle so that now the light comes up and bounces off at an angle so that you don't get light coming back to the receiver. But yet when the box isn't there, the light can come through to the receiver or to the reflector and get back to the receiver. So that's a way you can sense shiny objects with it. You could also do shiny objects which are cylindrical. If you think about a cylindrical object, as these go past this retroreflective sensor, because this surface is curved, when the light hits, it's going to be coming back at all different kind of angles. So it's very possible that one of those angles will have light getting back to the receiver. However, if you tilt and rotate the sensor, you can get, and you can see here we're tilting it and rotating it and putting the reflector on this side. You can usually get a good angle and a good adjustment on it so that no light gets back to the receiver when that shiny object is in front of it. There's also a thing when you're doing shiny objects called polarizing filters. And I will be honest with you, I do not understand light polarity, but I can explain it. So if you look at this particular set of sensors here, we have what's called a vertical filter and a horizontal filter. So light filters are vertical and horizontal. And you put a horizontal on one lens and you put a vertical on another lens. So if I have a shiny object, the light is going to come out in a vertical polarity and it's going to come back in a vertical polarity. The vertical polarity can't get through the horizontal filter. I sometimes use the Venetian blind effect, like if I had Venetian blinds which are slats like this, when the light comes through there, it comes through in slats. So if I had on the other end vertical blinds, that horizontal light can't get through those vertical blinds. And that's what this happens. So if I've got a shiny object on a retroreflective sensor, when the light comes out, it comes out and will be vertically polarized. It reflects off the shiny object. It comes back as a vertically polarized, but can't get through the horizontal filter, and therefore the sensor won't see it. However, the same sensor, when it sees its own reflector, the light comes out vertically, but because of the prism effect in the reflector, the light is rotated 90 degrees and comes back in a horizontal pattern or in a horizontal polarity, and therefore will go through the horizontal filter so the sensor sees the reflector. So it uses polarization filters to help with shiny objects, so it will not see the shiny object, but yet it will see its light coming back from the reflector. And again, you have to break the entire effective beam. Now there's proximity mode. And actually what I'm going to do at this point is I'm going to break this video at this point. so you can have a little rest, and I'll do it in a part 2 video.